In this video, we are going to discuss something that is both familiar but also new to us. This is Newton's first law of rotational motion. We already know the basics of Newton's first law, so all we need to do is redefine it for its rotational version. Even though I hope you remember Newton's first law from October or November, let's do a quick review. Imagine we have a box and we apply an 8 Newton, a 12 Newton, and a 20 Newton force to it, as shown in this free body diagram. How would you describe the motion of this box? What words would you use? These are the words that I would use, although there are probably many more, so if you came up with other ones, they're probably right. So the box is in equilibrium because the forces are balanced. This means that the net force, or the sum of all the forces, is 0 newtons. 8 plus 12 plus a negative 20 will give us 0. And because of these three things, this box will not experience any acceleration, so it will move with a constant velocity. Now, notice that I did not say that this box is at rest. Remember, we do not know whether or not this box is at rest. It could be, but all we truly know is that it is moving with a constant velocity. It could be a constant velocity of 0 meters per second, but for all we know, this is moving at 10 million meters per second. All we know for sure is that it is not accelerating. So hopefully, as you remember, Newton's first law is fairly simple. If the net force on an object is 0, then the object will not experience any acceleration, or it will continue to move at whatever constant velocity it has been moving at already. Turns out Newton's first law of rotational motion is very similar. If the net, or total torque, on an object is 0, then the object will not experience an angular acceleration. It will continue to move at whatever constant angular velocity it was moving at. You will see it is a direct parallel. No torque means no angular acceleration. A great example of this is a spinning top. Once we set it spinning, it will continue to spin at pretty much a constant velocity on its own because there are no additional torques on the object slowing it down. Of course, air resistance and friction are somewhat slowing it down, which is why eventually the top will stop spinning, but it does take a very long time. So spinning top, in essence, represents this. It's just going to spin at a constant angular velocity because there are no torques and no acceleration to slow it down. A big thing to remember, both of these objects shown here have a net torque of 0. Equal forces applied at equal lever arms are trying to induce equal rotation in opposite direction. Their torques are canceling each other out. Both of these bars are moving with a constant angular velocity. This one on the right just has an angular velocity of 0, but they are both still not accelerating, and they both represent a situation of 0 net torque. Let's look at how we would use the mathematical version of this equation. Sigma torque is equal to 0. Essentially, this means that if you add up all of the torques acting on an object that is in equilibrium, you should get 0. And to calculate the torque, you just need to do the force times the lever arm in a very basic situation. The biggest thing you really need to pay attention to is positives and negatives. This equation won't tell you the direction of the torques, and the free body diagram won't directly tell you the direction. In order to assign positives and negatives, you need to visualize which force is causing a positive torque, or a clockwise rotation, and which one is causing a negative torque, or a counterclockwise rotation. And then you can just include that in your torque calculations. The positives and negatives in terms of clockwise or counterclockwise doesn't really matter as long as you are consistent. In this diagram here, the 5 Newton and the 12 Newton are trying to induce rotations in opposite directions. So they do need to have opposite signs. But if you look at the equation, it doesn't actually matter which one you make positive and which one you make negative, as long as you recognize that they are acting in opposite directions. One big idea of this law, which most of you discovered during our meter stick balancing lab, is this. To keep an object in rotational equilibrium, smaller forces need to be placed further away from the pivot point to generate the same torque as a larger force. That is because a torque is the force times that lever arm. So to have a smaller force generate the same torque as a larger one, you need to be multiplying it by a larger number. And when solving rotational equilibrium problems, keep these things in mind. First of all, be sure that the value that you use for R or lever arm is the distance from the line of action of that force to the pivot point. Diagrams might give you lots of numbers, lots of dimensions. Make sure you are clearly identifying the correct one. Be careful with directions. Assign positives and negatives to the direction of the torque based on the direction of attempted rotation. Do not assume all torques are positive or all torques are negative. You really have to take a moment and think about what direction is this force attempting to spin the object. And you also have to take into account every force that is causing a torque on the object. You can't just choose to ignore one. If there are 8 forces causing torque on the object, you have to add up all 8. It's not only limited to 2 or 3. But one cool trick, any force that is acting through the pivot point causing 0 torque ends up just being a 0 in our addition equation, so you can ignore forces that are not causing torque. Any force whose line of action is acting through the pivot point.